Okay, so let's use induction to prove that 4 to the power n minus 1 is divisible by 3 for all n greater equal to 1. So this is exactly the claim that we just discussed. Okay, now, in order to discuss this claim more formally, let's introduce this predicate that we already had. So P of n is a predicate that takes n and returns the claim, the statement 4 to the n minus 1 is divisible by 3. Okay, and the claim we're making is that for all n greater equal to 1, P of n, we are asserting that P of n is true. Okay, now I want you to have a couple of analogies in mind as I go through this proof. The first is just an intuitive, get a feeling for induction. Imagine that, there's a line of people. The first person in line is a girl, and behind any girl is always a girl. Okay? So we could ask, is there anything but girls in line? Okay, and where could a boy be? Because the first is a girl, behind that's a girl, behind that's a girl, behind that's a girl. So everyone in line must be a girl. Okay, here's a more concrete analogy. So when you were all grown up and like 15, you like to assemble dominoes upright on the floor. So you assemble a bunch of dominoes and you painstakingly put the dominoes in a line. Okay, and they're close enough to each other. Let me label the dominoes 1, 2, 3, 4, 5, 6, 7, 8, and we could continue. And you're very proud of yourself. And then your little brother comes along and tips over this domino, and boom, all the dominoes tip over. So 1 tips over 2, 2 tips over 3, 3 tips over 4, and so on. Everything tips. Okay. Now, how do we know that all the dominoes tip? Well, for sure, we know that the first domino tips. Okay, so first domino tips, because that's what your brother did, your mischievous brother. Okay. Now, how do we know that all the dominoes tip? Relies on sort of the way in which you constructed this line of dominoes. You made sure that the dominoes were close enough to each other. So dominoes, consecutive dominoes are close enough to each other. Okay, and if you know that consecutive dominoes are close enough to each other, you tip the first one. We all know that all the dominoes tip. And you don't need to go and verify domino number 757. Did you tip? Yes, I can tell you straight away. Because all the dominoes were close enough, and you tip the first one, brrr, starts off a chain reaction. Okay. And induction is exactly that. It's a chain reaction. Okay. So let me show you how that works. So, last lecture, you should have proved the following claim. If 4 to the n minus 1 is divisible by 3, and then 4 to the n plus 1 minus 1 is divisible by 3. Now, if you didn't prove this, don't worry. We'll quickly prove this later on. But hopefully, you exercised your strength in your muscles in direct proof and actually proved this. Okay. But now let me phrase this in the language of my predicate P of n. So this is actually P of n, and this is actually P of n plus 1. Okay, and what you have proved, and you didn't need to know what n was. So what you have proved is that P of n implies P of n plus 1. And you didn't need to know what n was. So this is true for any n. In particular, it's true for all n greater equal to 1. Okay. So now what I'm going to do is I'm going to show you that, this is a lot of implications all contained in 1. In fact, it's infinitely many implications. For example, there's P of 1 implies P of 2. P of 1 implies P of 2. And P of 2 implies P of 3. So P of 2 implies P of 3. And P of 3 implies P of 4. And P of 4 implies P of 5. And so on. So you see, you set up an infinite chain of implications. Think infinite chain of dominoes. Very similar concept. Okay. Now, what do we know from these implications? Nothing. Okay. And that was the whole idea behind reasoning in the absence of facts. And we're hoping that someday a fact will come to light that'll help us actually learn something concrete. Okay, but for the moment, we know nothing. We just know that a bunch of links, bunch of relationships exist. For example, now if someone came and told me P of 3 is true, I can infer that P of 4 is true. Okay. Now, based on our tinkering, we saw that P of 1 is the claim 4 to the 1 minus 1 is divisible by 3. And this is clearly true because 4 to the 1 minus 1 is equal to 3, and that's clearly divisible by 3. So P of 1 is true. We have a new fact, and that fact is going to make this reasoning in the absence of facts all worthwhile. Because look, what this says is that this guy is true. So I'm going to box him. I'm going to box him in blue. That guy is true. Okay? So it's now a known fact. But because that guy is true, and we already proved this implication, P of 1 implies P of 2. And if the left side of an implication is true, we can infer the right side. So we can infer P of 2 is true. But wait a minute. P of 2 is true. So we can infer P of 3 is true. Wait a minute. P of 3 is true. P of 4 is true. You see the chain reaction? Boom, 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 boom. It goes on forever. Just like the chain reaction in the dominoes. In fact, it's basically the same. Okay. The equivalent of tipping the first domino, the equivalent of that is showing that P of 1 is true. So establishing that P of 1 is true is analogous to the first domino tipping. Okay. And establishing this link, P of 1 to P of 2, P of 2 to P of 3, P of 3 to P of 4, establishing all those links is exactly equivalent to the requirement that the dominoes must be close enough to each other. That link is the formal definition of close enough. So P of 2 is close enough to P of 1 such that if you tell me P of 1 is true, I can infer P of 2 is true. That's exactly what an implication does. It puts a link that places them close together. Okay? So you see, this set of implications, which set up this infinite chain, which was useless before, once I add the ingredient that this guy is true, boom! All the predicates for 1, 2, 3, 4, they all topple and they all must be true. So, in a sense, we have proved that all the predicates are true for all n on the right-hand side of this P of 1. Okay. And that's very nicely summarized in the principle of induction. Now, it turns out that the principle of induction, we can prove it, but we won't for the moment. Okay. It can be proved from the well-ordering principle. So I'm just going to state it now. This is the intuition behind the principle of induction. Okay. And we're just going to use it. And then at the end, I'll illustrate to you why, the principle of induction and the well-ordering principle are more or less the same by showing you that things we can prove with induction, we don't need induction. We can just use the well-ordering principle. And in fact, you can prove the principle of induction from the well-ordering principle, which, if you're interested, look into the text. Okay. So, let me summarize this discussion in the principle of induction. Oh man! Humanity's greatest invention. Okay, principle of induction. Okay. So, from the very beginning, we must agree that we're working with some predicate P. So we're working with some predicate P, okay, and I'll just say, so P of n, a predicate. We have a predicate in mind. So we have a predicate. Okay, and then the principle of induction says, so for this predicate, if you have established P of 1, okay, so you have established P of 1. Okay, so this is called the base case. Because it's the first thing that you have established. This is called the base case. And you have established, or you have proved, or you have shown, you have proved P of n implies P of n plus 1 for all n greater or equal to 1. So you have proved this in general without knowing anything about n. So you proved it for any n greater than or equal to 1, which is what I assume you proved in the last lecture. Okay. Then, effectively, what the principle of induction says is you set up this chain, and by toppling this P of 1, by establishing this P of 1 to be true, you've set up the chain reaction, and that chain reaction goes and establishes the truth of all the remaining predicates for all n to the right of this 1. So what the principle of induction allows you to now do is to conclude. You can conclude by induction, by the principle of induction, that P of n is true for all n greater or equal to 1. That is the principle of induction. Okay, and usually establishing this second step here is called the induction step. Okay. So let me show you, let's get a little bit familiar with the principle of induction by showing you a few variants of this. Okay. So remember, so examples, some variants, just so that we sort of understand what's going on. Suppose, so examples or variants. Okay, so suppose instead of P of 1, you established P of 5. Okay, but you also proved that P of n implies P of n plus 1 for all n greater equal to 1. Okay, so you've established, not quite the base case that was asked for, okay, but you've established the links, you've established the implication. So let's see what this implication links, tell us. They say that P of 1 implies P of 2, implies P of 3, implies P of 4, implies P of 5, implies P of 6, implies P of 7, implies, and so on. Well, but unfortunately you didn't establish P of 1, which is what the principle of induction asks for. But you did establish P of 5, so all is not lost, it turns out. So you did establish P of 5. Okay. So from P of 5, well, we don't know anything about 1, 2, 3, and 4, but you did establish P of 5, but that's nice. It's not, all is not lost, because now P of 5, we know implies P of 6. So you've set up the chain reaction, P of 6 implies 7, and so on. So you've set up the chain reaction. The only difference is it doesn't start at 1, it starts as 5. Okay. Now if you go and separately manage to prove these guys, then okay, you've established for all n greater equal to 1. But still, establishing for 5 and then all the links allows you to prove it for infinitely many n. Okay, that's interesting. Let's see if we reverse the roles of the 5 and the 1 here. Okay. So suppose, let's see what happens if you proved P of 1, okay, which is what the principle of induction asks for. But you only establish the link for n greater equal to 5. Okay, so it's a different scenario. Let's list the links. So anytime you have a situation like this, you can just list the links. See what is the chain that's being set up. So P of 5, n equals 5 implies 6. So P of 5 implies P of 6. And 6 implies 7. And 7 implies 8. And so on. But now here, sitting all alone, hanging around, are P of 4, P of 5, P of 3, P of 2, and P of 1. Okay. Now, okay, you've also established P of 1. So we'll put that in a blue box here to say that, oh, okay, we know that P of 1 is true, but that's not a lot of help anymore. Not like the previous case. Okay. Because what? From P of 1, there's no link to P of 2 anymore. You haven't established that link. So all you can conclude here is that P of 1 is true. You don't know anything about any of the other guys. So, in other words, establishing P of 1 fails to set up a chain reaction in this scenario. In order to set up the chain reaction, you must establish the truth of one of the propositions, one of the predicates, P of 5, for example, and you must set up all the links. Okay, so that's very important. And usually when, an induction has gone wrong, and you can see some examples in the text, either, so bad induction or induction gone wrong, either you have the wrong base case for setting up the chain reaction. So in this case, a base case, so if you have proved P of 5, you would set up a chain reaction. Okay, that would allow you to conclude from 5 onwards, and you could prove these separately. But this is the wrong base case. So induction gone wrong, either, wrong or no base case. Okay. Okay. Or you haven't proved all the links. Imagine, when you made this argument, you must not assume anything about n other than the fact that it's bigger than or equal to 5. If you only prove this link for 5, 6, and 7, you don't have this link, and not having this link breaks the infinite chain reaction. So you have to establish so wrong or no base case, or not all links proved. So in either of those cases, the induction is just wrong. Okay? There's no way to resurrect it except for getting the right base case and proving all the links. Okay? So now, with the principle of induction in hand, let me show you how induction works in terms of what's the induction proof mechanics, and we'll use the induction proof mechanics to prove exactly this claim. Okay. So now we are ready to prove this claim. Okay. And so we usually say proof by induction. This tells the whole world that you're about to use the induction principle, okay, the principle of induction. And so what you're going to do is you're going to establish the base case, and you're going to establish the induction step, which is an infinite chain of implications for all n greater or equal to 1. And once you have done that, the principle of induction allows you to conclude it's true for all n greater or equal to 1, and you're done. Okay. So it's usually helpful to restate the predicate. So let's restate the predicate. So our predicate, our claim is P of n, is the claim that 4 to the n minus 1 is divisible by 3. Okay. And now the proof is by induction of this claim for all n greater or equal to 1. So let's establish the base case. P of 1 is the claim that 4 to the 1 minus 1 is divisible by 3. Okay, what is that saying? That's saying that 4 minus 1, which is 3, is divisible by 3. That's clearly true. So P of 1 is true. Okay, that's the first step in the principle of induction. Now comes the complicated step usually. So this is called the base case. And this is called the induction step. Okay. Now we have to prove, must show P of n implies P of n plus 1 for all n greater than or equal to 1. So that basically means we can't assume anything about n, so we have to prove it for a general n, okay, except that we can assume that n is bigger than or equal to 1. Now, this is the proof of an implication. So we have to use one of the methods for proving implications. Now we have two methods. We have the direct method, or you can use contraposition. Okay, but it's important to make sure that you use one of these proof methods to prove an implication. And so we're going to use the direct method here. So in using the direct method here, and that's by far the most popular, the most common type of induction step, is the direct proof of an implication. So what are we going to do? In the direct method, we assume that this left-hand side is true. So we get to assume P of n is true. Well, what is that assumption? That's the assumption, okay, that 4 to the n minus 1 is divisible by 3. We must show the right-hand side is true. That's why. Because that's the mechanics of a direct proof. We must show that P of n plus 1 is true. Okay, why? Because that's the mechanics of a direct proof, and P of n plus 1 is the right-hand side of this implication. What must we show? We must show that 4 to the power n plus 1 minus 1 is divisible by 3. Ah, interesting. Okay. So, we start with the left-hand side being true. We get to assume this. What does that mean? That means that 4 raised to the power n minus 1 is a multiple of 3 if it's divisible by 3. So it's 3k. Or this means that 4 to the n is equal to 3k plus 1. Okay. Now, that's the beginning of the proof of this implication. Okay. We know where the end is. The end must be to show that 4 to the n plus 1 minus 1 is divisible by 3. So that's the end of the proof. And so, I must end the proof by showing, therefore, P of n plus 1 is true. Okay, so that's the end. So it's kind of cool that I know where I'm going. I know what the end of a direct proof must look like. Okay? And I'm here currently, and I need to go here, which is a claim about 4 to the n plus 1. I have 4 to the n, and this is the creative step in an induction. Okay? Is to link what we were allowed to assume, that 4 to the n is equal to 3k plus 1. We have to link that to where we are going. Okay, we know what we're allowed to assume. We know where we are going. So hopefully creating that link is not too hard. Okay, in this case, it's not too hard at all. Because look, I'm interested in an expression involving 4 to the n plus 1. So I have 4 to the n. So I can just multiply both sides by 4. So multiply by 4. Okay, and that gives me 4 to the n plus 1 is equal to, multiply this side by 4, 12k plus 4. Or, if I subtract 1 from both sides, 4 to the n plus 1 minus 1 is equal to 12k plus 3. Okay. But that is equal to 3 times 4k plus 1. So 4 to the n plus 1 minus 1 is a multiple of 3. 4 to the n plus 1 minus 1 is divisible by 3. And that's exactly the claim. Therefore, P of n plus 1 is true. 4 to the n plus 1 minus 1 is divisible by 3. Okay. And that is the end of the proof. Actually, typically we'll say, therefore, P of n plus 1 is true. So, by induction, P of n is true for all n greater or equal to 1. And here we're invoking the principle of induction because we've shown 1 and we've shown 2. Okay, now some notation. So this is the base case, this is the induction step, and typically this assumption that we make that P of n is true, this is sometimes called the induction hypothesis. Okay. So in any induction proof, and we're going to see more examples, in any induction proof, it is absolutely necessary to have the base case. If not, your proof has gone wrong. It's absolutely imperative to prove the implication without making any assumptions about n, except that n is greater than or equal to 1. So in other words, to prove it for a general n. And you can prove this implication using either a direct proof or a contraposition proof. Here we use the direct proof. So this is the direct proof. Okay. Now let me emphasize that in the induction step, you must prove P of n implies P of n plus 1 for all n greater or equal to 1. For all n greater or equal to 1. Okay. So, in other words, effectively I'm proving infinitely many things. For n equals 1, I have to prove this implication. For n equals 2, 3, 4, 5, 6, and so on. And the way I do it is by not making any assumptions about n, by treating n as a general n. Okay. And then you might wonder, well, so I have to prove infinitely many things. So why don't I just forget about induction and just prove P of n for all n bigger than or equal to 1 from the get-go? Because that's also proving an infinite number of things. P of 1 prove P of 1, prove P of 2, prove P of 3, using a general n. Okay. And that is the power of induction. Okay. It's the fact that you don't have to prove P of n, which is typically hard. You have to prove an implication, and proving an implication is much, much easier than proving the original claim. And why is that? Okay. It's much easier to prove an implication, and that's because in the proof of an implication, that's reasoning without facts. So we don't need to know if P of n is true or false. P of n plus 1 is true or false. We have to prove just a link. And the way that materializes in the proof is that we get to make an assumption. So to prove an implication, we get to make the assumption that this is true. And that's a huge bonus. Okay? It gives us something to work with. Something to start at, gives us something to start at and make our way towards P of n plus 1. Because we only need to prove the link. Okay, it's much easier to prove the link because we get somewhere to start at. Okay, now, yes, we have to prove infinitely many links, so we do it for a general n. But it's much easier to prove a link than P of n. Okay, but there's a price for this much easier proof of a link. And what's the price? Well, it's usually a very small price. We've added the need to prove P of 1, the base case. There's no base case here. You just prove them directly if you want. Okay, but induction says, you don't need to prove them all directly. You can prove the link, okay, and then the base case. And you're done. The link is much easier to prove. Okay, let's do some examples. Let's erase first using speed erase. Okay, and in these examples that we're doing, we're going to see that, induction can be used to prove incredibly general things. Sums, inequalities, divisibility, and even more complex things about, strange-looking problems that seem to have nothing to do with math. Okay, yet induction is the way to prove it. So let's erase. And then get back to some examples.